Hello, and welcome to today's webinar, GNSS Interference Detection and Mitigation for UAV Navigation. Brought to you by GPS World and our sponsor, Loctronics Corporation. I'm Bethany Chambers from North Coast Media, publisher of GPS World magazine, and I will be your event manager. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. The recording will be available 2 weeks from today on our website at gpsworld.com/webinars. A link to the on-demand recording will also be emailed to you when it is available. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice in the lower left-hand corner of your console that there is a Submit button. We encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in queue. Questions that were submitted during registration may be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World magazine or in one of our e-newsletters. We strive to answer as many of your questions as possible. Finally, if you experience any technical difficulties during today's event, select Help to submit your issue, and Assistant Producer Diane Safranik or I will personally assist you. Now I'd like to turn today's event over to our host, Dr. Mike Matthews, CEO and founder of Loctronics Corporation.
Thank you, Bethany. Hi, welcome everybody. We are very pleased to bring you an interesting lineup of speakers and topics today covering GNSS interference challenges and solutions for UAV navigation. Delivering reliable navigation information in denied environments is fast becoming a critical issue both in commercial and military UAV applications. The availability of relatively low-cost, easy-to-acquire jammers has already caused a significant increase in unintended interference, with many cases going unreported. Continued reliance on low-cost GNSS COTS-grade sensors is no longer a practical consideration for any UAV platform having significant value or operating in areas where deviations from planned courses can risk properties and lives. It is not a stretch to say that next-generation navigation systems must include multiple sensors and improve interference detection and mitigation capabilities. Frank Boynton is our first speaker, and we'll be discussing GNSS interference denials and needs and challenges. Frank has been with Navtech GPS since 1998 and spearheads the company's involvement in numerous projects for U.S. military organizations, private corporations, and educational institutions. Without further ado, Frank, why don't you take it away, and we'll get started.
Great. Thank you, Mike. I think some of the first comments that you made are very appropriate for where we are right now. It is really indeed a hot topic, jamming interference to GNSS, not just GPS, but all GNSS navigation systems. One of the things that we do is we go around the country and we have booths, stands in different shows, and that is inevitably what comes up eventually. Well, what are you going to do about jamming? What's out there? What can we do about it? So we're going to talk a little bit about that and exactly what it is that we can do to answer those questions. So I'm going to just go ahead and jump right into it and start talking about some of the vulnerabilities. It's obvious that GNSS is susceptible to vulnerabilities for different attacks. Some would be intentional jamming, and then there's unintentional jamming, and we will get into that a little bit later on. Usually when we think of jamming, we think of intentional jamming or warfare, electronic warfare, but that's not always the case. We do need to keep out and keep alert as well for unintentional jamming sources because they are out there also. So the received power of GNSS signals at the Earth's surface is very low. I have some figures up there about exactly how low they are. And if you want to put that in kind of a context that's a little bit easier to understand, you see the two Christmas tree light bulbs down there. The GPS signal and most GNSS signal, it's kind of like looking at two Christmas tree light bulbs with the naked eye from the satellite on the Earth. You're just not going to see it. The signal is under the noise floor, and we do a lot of tricks inside the GPS receivers in order to pull out that signal from under the noise floor. GNSS signals are intentionally protected spectrums, or internationally protected spectrums. That is recognized worldwide, and everyone on Earth knows not to get inside of GNSS spectrums. They are protected. GNSS signals, however, because they are so low, can be fairly easily overpowered. So it's something that is really top of mind. It's not a very difficult thing to do as far as jamming. The GPS frequency received at Earth for L1 is about minus 160 dBW. Galileo is a little bit stronger than that at minus 152 dBW. And GLONASS is right around the GPS frequency gain at about minus 161. And these are all received at Earth, a little bit higher. Higher you go, of course. So jamming can occur at any frequency in any location, not just GPS, but any radio frequency can be jammed for the most part. The other vulnerability today, where we are, is that most receivers and antennas are not built with strong AJ qualities or anti-jam qualities, except for those that are put out by the military. However, civilian GPS or civil GPS user sets don't have strong capabilities for that. The other type of jamming is called spoofing. I'm going to call it jamming, but it's actually spoofing, which can be just as dangerous or even worse. It's a denial of the actual signal replaced by a pseudo signal. So in other words, someone will take a generated or synthetic GPS signal and attempt to replace that real signal on a UAV or other vessel while it's on its course. This is typically not a problem to, it's typically a problem to non-SAASM receivers. They don't have that capability. This is not something that's easy to do. Jamming is going to be a little bit more easy. There's different things that they can do, different ways to do it. However, spoofing is not quite as easy. It's a little bit more difficult. What they do is they try to mimic the GNSS signal. However, it has to be in real time. There has to be a smooth transition from the real GPS signal to a false GPS signal. So from there, it also must stay locked on. So, this is what they've used and have used to claim to have hijacked some of the UAVs in the past. There are many types of jamming techniques. I'm not the expert on this field, but I'm just going to give you an introduction as to what they are, and I think that Pete McDorn and others will get into this a little bit more later on. There's matched spectral, and I've kind of put these in order of how dangerous they are. First, we have matched spectral, where you have the signal with the same power spectral density as the target signal, and they come in very, very close and mimic very closely what the signals or the GPS or other GNSS might look like. And then from there, we go into a chirp or sweep, and those are short bursts where the frequency of the center carrier is changed with respect to time. Then we have random noise, which is a more broad spectrum, just noise with broad amplitude and bandwidth in order to jam the signal. Then you have carrier, which is a specific tack on the narrow band of a specific carrier frequency. Then you have natural interference as well. So that's, again, now where we look at something that's unintentional. Usually it's very low, including solar flares, scintillation, that type of thing. We don't usually think of that as jamming, but it is jamming. It's a little bit of Mother Nature's interference. So with all these techniques, though, it is still possible to read through parts of the actual signal, process, and pull it through. And that's what we're going to talk about a little bit later. When we talk about intentional jamming, we're really talking about things, kind of the top of the list, and one of the things that we worry about most is electronic warfare. From there, we move on to terrorism, and then self-preservation and evasion. What we mean by that is, the example that was given, I think, a little bit earlier, the Newark, New Jersey airport, where there was a van that was driving by it every day, and the purpose of the jamming was not to jam the airport signal. The purpose was self-preservation. There was a guy in there. He was in a work van and didn't want the boss to know where he was, so he simply turned a jammer on inside of his vehicle and drove around so the GPS couldn't be tracked within his vehicle by his boss. So unfortunately, this self-preservation act caused a lot of problems for a lot of people. They did eventually find the person, and they took care of it. Security is another reason. Someone might not want a person of interest or a VIP for a location to be known via cell phone or other tracking devices. Spoofers as well. Again, we talked about that a little bit, which is basically if someone has any type of vehicle or a person or any GNSS, they want you to think you are somewhere that you're not, and that can also be used to steer as well. Intentional jamming, I've put light squared under here as well. That can also be unintentional. However, this was a case where there was a frequency that was out of band of GPS. However, it was going to originally be broadcast from space. They got licensed to broadcast it from Earth at the same power, and it was simply going to overpower the front end of the GPS receivers. And I mentioned that it's intentional because they knew this existed, yet they were going to push it through. So we do have to be careful. This was not on GPS frequency. It was beside it, but the power was very high. And the lesson learned there is light squared may be gone, maybe not gone. However, there will be others. And that's a very valuable frequency that's sitting there, and it will be used by somebody. Just a quick story. You see a few of the jammers there. The problem with some of these jammers are that they're really not regulated. The 200 milliwatt personal jammer that would go in a car, you plug it into your cigarette lighter, those aren't regulated. They're just built. Sometimes they cover the bubble of your vehicle. Sometimes they cover the bubble of an entire block. Sometimes they cover much more than that. So they're not regulated, and we don't know what they're going to do and what they're going to cover exactly. From there, we go to unintentional jamming, and you'll notice that we also have a couple of pictures that have carried over as well. Excuse me. So sometimes these reasons are not obvious. The unintentional jamming, some of it does happen out of band interference. We also have harmonics as well. You can see there a picture of a 900 megahertz antenna in the center there. I had a case where I put a GPS system up on a building a few years ago. Everything was working great. A year later, I got a call from the client, and they said, hey, our GPS system's no longer working in our building. What's going on? So I flew out there, went to the top of the building, and noticed there was a large 900 megahertz antenna that had not been there before, and was able to point to that as the problem and was able to fix it. You can also have a bad LNA, or low noise amplifier, within the GPS receiver, and that can loop back and cause other problems as well and jam other GPS receivers in the area. Also, just another bad amplifier component in a non-related system. I just had a case where I went down to a client a couple months ago, and they were being jammed by a PA system. They had their PA system was on. There was something wrong inside the amplifier, and it was broadcasting dead on L1 GPS at 1575.42 megahertz. It was a very low transmission rate. Was going very short distance. However, it was jamming their GPS that they needed. So GPS jamming can hide in a lot of places, intentional or not. Cell phone jammer that's listed as well. You see that on the picture. There's a jammer there with multiple antennas, and they're for multiple reasons. There was a case where in a church there was a preacher who was tired of people's cell phones ringing and texts coming in during services, so he got this cell phone jammer. However, unbeknownst to him, he did not know that there was also a GPS jammer on there, and happened to be someone there that had a jammer detector and was able to find this. So it occurs in all kinds of places, expected and unexpected. So I'm running a little short on time. We're going to go through this a little bit more quickly. So as far as UAVs, we're going to kind of look at that a little bit more. Intrinsically, UAVs have some advantages at elevation, not so much when they're flying in cities, but they're up in the air. That means that typically, typical jammers are ground-based. You can put them in the air. Your GNSS antenna is going to be on top of the vehicle, so there's going to be some intrinsic value there where the jamming from beneath will be blocked a little bit. You're also going to be a distance away, which helps having some space between you and the jammer. And it can also detect in the void. So if the UAV has a detection system on it, it can usually go around. Ground vehicles don't usually have that, but can happen. What does the U.S. military do and some of our allies? Well, they use SAASM for the most part, Selective Availability Anti-Spoof Module, which is built specifically for this. You can also use IMUs, which if there is jamming, you can carry over, let it know, and go on the IMU instead of using the GPS, and that will push through it a lot. There are also multi-frequency bands within GPS. We have not only L1, L2, but others, and you can switch over to those. There are also anti-jam antennas, nulling SERPA antennas, as well as filtering. Civilians can use most of those for the most part. We don't have access to all of those great military features. However, we do have a lot of them. We can go to other frequencies as well. So we have not only L1, L2, we have L2C, L5, and civilians can typically also change constellations. We also have GLONASS, Galileo, and the upcoming Compass as well. So I'm going to go ahead and hand this over to Mike, and he has a poll question for you.
Thank you, Frank. Up next will be Pete McDoran, but before we do that, I would like to go ahead and ask the audience a question. And basically, how would you categorize your interest in GPS GNSS interference detection mitigation? I will push the poll results here in a second after people have had a chance to answer. So that's very interesting. So right now, 64% of you are actually researching the issue. Very good. We're going to do polls at between each presentation. So let's see. Up next is Pete McDoran, and he's Chief Scientist for Electronics Corporation, and will be discussing GNSS interference and attack mitigation. Mr. McDoran has more than 30 years of technology development and integration experience in GPS and is the principal inventor of codeless GPS, a precursor to electronics' own SCP technology. Pete, take it away.
Okay, thank you, Mike. I want to make the point that the subject here is really being addressed from the point of view of small UAVs, probably in commercial applications, and because a lot of the possibilities for surviving in the world of attack and interference, a lot of those things aren't applicable to small platforms. The slide here regarding the mitigation, there are two broad categories called, one, trying to keep yourself out of trouble, and the other category is what are you going to do when that isn't enough. The idea of notch filtering, that goes back to the times of World War II, when you're really dealing with continuous wave jammers or narrowband electronic attacks of some sort. However, when you are out on the internet and you just happen to type in GPS jammers, you're going to see that there are hundreds of links. And those links take you to devices that are intrinsically wideband, and they are already targeting multiple of the GNSS constellations. The SAASM, the Selective Availability Anti-Spoof modules that go into the DoD receivers, they require NSA ComSec authorization and thus are not at all available for commercial applications. The null steering, the so-called SERPA antennas for control radiation pattern antenna, requires additional hardware. It's going to require some power. It's a larger form factor than the little GPS antennas that you can hold in the palm of your hand, and cost is an issue. The idea of going to multiple constellations at multiple frequencies, that's attractive, could have value, but I will bet a beer that the jammer suppliers will adapt their products to continue the mischief. And we'll get into that more a little bit later on. So the preferred strategy is to believe, and I think with real justification, that jamming and interference will be a fact of life in the future. And our strategy is to design to survive the attacks. And we'll show data on how that's done. Let's look at some examples here of something you can get right off the internet. And this is really at the very low end of power. This thing, under most circumstances, is going to be right at the noise floor of anything going around trying to find it. And so we're picking a value of 4.5 milliwatts. For comparison, your cell phone runs at about 100 milliwatts. And that's of effective isotropic radiated power, and at a frequency of L1 typically, and some of these bandwidths are up at 50 megahertz wide. Now what that means is that everything that shows up at L1 is covered up with this, whatever that attack is. And in this case, it extends so far away from L1 that it actually takes out half of also the GLONASS channels. These jammers typically are cheap. They are in the range of about $30 to $300, and so as you can see, mischief is cheap. Now in this 4.5 milliwatt, there is a typo down here at saying that it causes acquisition difficulty out to 117 kilometers. That would be the case if you went to the most powerful of the internet jammers, which is 600 milliwatts. But at a low power jammer, that instead of 117, it should say it's about 10 kilometers. And we'll get into that a little bit more later. A typical commercial off-the-shelf GPS receiver has jamming tolerance of about 20 dB of jamming to signal power, and we'll be dealing with that a little bit more here. So in the category of exploring how you're going to answer the challenge, there are alternative signal processing techniques. And to achieve that resilience, we have gone after a category of performance that is similar to the way that the DoD has arranged the so-called Dagger receiver, of which there are now tens of thousands deployed. And that has a superior signal jammer performance. The desired additional performance that we're going after in our designs is in the category of 15 to 20 dB relative to what a commercial GPS receiver currently performs. So part of the strategy is to detect early on what it is that you are being challenged with an attack. And that's done by monitoring the power that is in the channel of interest for whatever constellation you're looking at. And there's issues, some kind of a threat alarm, and there's strategies for a seamless transition to survive. Let's look at a concept that I call the signal acquisition denial zone that is created by these jammers, and I just call it a SAD zone. You can think of any kind of emoticon that comes to your mind to put on the display when that happens. Consider again the 4.5 milliwatt jammer situation, and keep in mind that this thing is going to be even smaller in mass than a a weather radio sonde balloon package that flies on weather balloons. Those things go up to 30-kilometer altitudes and fly for about 3 hours. You could implement this in a package that is probably just a fraction of the 9 ounces that flies as a radio sonde, and so therefore it is easily launched on a balloon. A commercial GPS receiver encountering this low-power jammer will have a SAAD zone that is 320 square kilometers. With a better performance that we are achieving in our designs, we can get 35 to 40 dB of J to S performance, and that will reduce this SAAD zone down to about 2 square kilometers. So let's take a look just at a diagram here. On the right-hand side, there is that tall green bar there at 320 square kilometers, and that is 20 dB of signal to, or jamming to signal power. And we're designing down to that little zone there between 35 and 40 dB. So if you look on the left, there's a big circle out there, and that represents the 320 square kilometers. The little red circle in there is where we will get within about 1 kilometer of the jammer. And therefore, based on that 1 kilometer of being right up near the offending package, that also gives the opportunity to geolocate. But keep in mind that the adversary has a big advantage here. It's cheap and easy to pull these off. And the idea that you are going to have a quick response to go out and get these things, particularly when there may be dozens deployed, it is impractical to have some kind of a response that eliminates the offending signals. So you've got to figure out how to live with it. The next slide, just for a bit more scale, this is just right in the Seattle area. Imagining if you had a balloon-borne 4.5 milliwatt jammer flying that came out of Seattle, that that outer circle is at 10 kilometers, and we would be able to, from the 10 kilometer zone, we can get within 1 kilometer of where that offending thing was happening, but just for scale. The last of my slides here is a suggested list of references that you could follow for your reading edification on this most challenging problem. So, Mike, back to you.
Thank you, Pete. Up next, I'll be giving a short presentation on our HGX receiver technology, but before I do that, I'd like to go ahead and throw out another poll question to the audience. The question is, what aspect of GNSS GPS interference detection, mitigation, location do you have a specific interest in? Detection and identification, mitigation and robust navigation, or interference source geolocation? Go ahead and submit your answers, and I will post the results here in a few seconds. So it looks like the majority of the audience has an interest in mitigating and getting robust navigation solutions. Very good. So I'm going to talk to you today about our HGX receiver platform that we're developing here at Electronics. And it's a hybrid solution that combines our SCP technologies together with traditional code correlating technologies, with the primary goal of increasing reliability and robustness of commercial-grade GPS receiver in interference environments. When we started the project, we launched with a basic set of requirements that we wanted to develop new receiver capabilities that had the ability to do basic interference detection, as well as provide good mitigation capabilities to allow it to operate in areas where conventional receivers alone would not operate. From an interference detection point of view, we wanted to be able to measure jamming signal and also be able to distinguish it from ordinary obstructions. In this case, where the receiver might be driving underneath a bridge or be obstructed by an embankment or urban canyon type problem. We also wanted to be able to monitor that interference across multiple bands and channels of the GPS and GNSS systems. In terms of mitigation capabilities, we wanted to increase the margins of the commercial receiver at least 15 to 20 dB over what conventional receivers would support today, and as well as provide standard integrated inertial so that if you lose your RF positioning, you actually have a backup solution. We also wanted to incorporate multi-frequency and ultimately GNSS capabilities so that if the other systems are available, you can switch to them if it is suitable in terms of what's going on. Long term, we'll also be looking at introducing signals of opportunity so that if all your GNSS fails, you can actually fall back to even stronger signals, digital television, potentially even the jammer signals themselves, to allow you to provide some additional navigation information while you're operating in the interference environment. Long term, the company is also focusing on attack characterization, where we'll actually provide more additional information about the type of interference attack that's occurring, as well as the ability to then ultimately locate it. The hybrid HGX navigation sensor it combines SCP technology with traditional code correlation technology using what we like to term as a moderately coupled, not tightly coupled integration through a federated filter system that also incorporates inertial sensors, which continuously monitors multiple channels, bands, and frequencies and observable types to develop a complete picture of what the navigation situation is for your navigation sensor. The basic architecture that we're making available this summer is going to be in an SDR form factor for preliminary testing and evaluation, which provides the HGX SDR sensor in a C++ based implementation that will run on Windows and Linux based machines, but also can be ported to embedded environments if you want to go mobile with it. In addition to that, we're providing this all on top of our advanced software radio platform, our ASR 2300 and ASR Workbench, which I'll mention briefly here in a second. And we'll be including tools to allow you to test and evaluate receiver performance in interference simulation and various scenarios that you might encounter in commercial jamming interference applications. I'm going to cruise through, we're a little short on time, so I'm going to cruise through my presentation to give us Michael Davies a little more time to present. He's actually got some test results which are far more interesting than probably the nuts and bolts elements that I'm presenting here today. The ASR 2300 is Electronics MIMO SDR platform, which we developed specifically with the idea of doing SDR GNSS applications with integrated inertials. The basic unit is a 2x2 transceiver, which can operate between 300 and 3.8 gigahertz, especially for L1 GPS processing. We also include on that an inertial package that allows you to do basically commercial and consumer grade IMU type implementation. There are additional interfaces available from expansion ports if you want to add a high quality IMU to the unit as well. The neat part about the ASR 2300, it's about the size of a pack of cigarettes, or excuse me, I should say deck of cards today. And it is actually great for laboratory testing, but we've actually used it successfully quite a bit in the field and continue to test with it all the time. Another part of our basic solution is ASR Workbench, which is the integrated development environment that we use and host all of our tools and platform kits. And it comes with you when you get the entire package. For those of you who have been involved with electronics in the past, my quick spiel on SCP technologies is probably very familiar. But SCP is essentially an outgrowth of codeless GPS technologies developed by Pete back in the 1980s. The basic idea is that we want to process signals without having to explicitly demodulate them or know something about them that would require us to go through a complicated demod process. Basically what we do is apply a simple nonlinear algorithm that allows us to go after and track the various sinusoids that those signals are comprised of. In the case of the GPS, this could be the carrier, it could be the L1CA chipping, could be the PY chipping, could be the L2C chipping, it could be any number of different signals that we're interested in that allows us to then track with a single SCP channel all satellites in view. And the real benefit of this technique is that it allows us and provides us the ability to do very long, coherent integration of the signals, which turns out to be a significant advantage when you're trying to deal with interference situations. One of the things that we're very excited about hybridizing SCP with correlation technologies is that the additional overhead required to implement an SCP sensor capability within a traditional GPS receiver is insignificant. It's less cost than adding an additional code correlation channel in your receiver. And so if you want to add P, PY, CA, SCP, L2C, SCP, GLONASS, Galileo, you really only have to add an SCP channel per data observable type that you're interested in. So to support multi-frequency capabilities, to support precise positioning surface capabilities, it's very easy in terms of additional overhead to add these capabilities to your receiver. Basically, we're in testing right now and finalizing our basic receiver implementation, and we're seeing some actually tremendous results. We are seeing the receiver produce enhanced jamming margin. J/S is at 15 to 20 dB compared to conventional GPS. And the multi-frequency stuff is still in development, but we're actually seeing that come online as well. We're planning on launching the first versions of our product this summer, and it will be available in a toolkit and evaluation kit form factor, targeting embedded development, and it will probably be only for GPS initially. If you'd like to see a preview at it, we encourage you to stop by at JNC this summer, June, at Orlando, and we'll be in booth 31. I'm going to do another quick poll question and then hand off to Michael Davies to do a presentation of the test results. And I want to make sure, let's see, what aspect, so this is what, there we go. What level of technology integration are you most interested in? How many questions do I have left? And let's see, we're at 38 minutes. I've got 2 more poll questions. I think I'll go ahead and do one now, and then we can spend more time in Q&A. So I'm going to push another poll question to you. What is your target application sector? Mil-aero, law enforcement, agriculture, GIS, other commercial? Okay. Wow, we got quite a bit of diversity on that one. That's cool. Yeah. This is a very telling slide talking about the growth in the sector for UAV applications in general. It's becoming very exciting out there about seeing the growth of different applications that people are thinking about for using the technology. Very good. All right, up next we have Michael Davies. And Michael Davies is a senior engineer for Electronics Corporation. He's actually more than a senior engineer. And he will be presenting preliminary test results for our HGX navigation sensor. He's a principal engineer on our HGX sensor team with technical expertise covering a wide array of technologies, including DSP design, PNT estimation, and Kalman filtering. Without further ado, Michael, take it away.
Okay, well, thank you, Mike. I'm going to talk about some preliminary test results of our HGX navigation sensor. And this first slide is to give you a taste of what we've been doing to test the HGX. We actually collected real-world data outdoors using our software-defined radio hardware platform. And we simulated a jammer. We didn't go outside and physically jam GPS, because that would be illegal, but we added in a software-simulated jammer to those raw sample streams, and we tested the HGX to see if we could survive a jam attack. And this plot is basically what we did. We drove around in a loop, and we tested the HGX receiver. And I'll talk about how we generated this plot a little bit more detail in the next few slides. So we didn't buy a jammer online and go outside and jam GPS because that would be illegal. So we simulated a jammer through software, and we added that simulated jammer to the raw data streams that we collected outdoors while driving around Woodinville, Washington. And what we ultimately wanted to do is we wanted to process that raw data with our GPS code correlating GPS receiver and our hybrid GPS receiver, or navigation sensor is what I should call it. And the figure at the bottom of this chart shows you how we did it. We drove around and we collected data using the ASR 2300 hardware platform to collect L1 GPS IQ samples, and we stored those samples on a hard disk drive. After the fact, we did our signal processing. That's where we added in our software simulated jammer, and we processed those samples in two ways. The first way was with our software-defined radio code correlation receiver, and then the second was with our hybrid receiver, so we could compare the performance between these two systems. So we collected data in a 10-minute loop by driving around Woodinville, Washington, which is about 30 minutes away from downtown Seattle, and we used our ASR 2300 software-defined radio hardware platform to collect these GPS samples and write them to a disk. And you can see a picture of that on the bottom right side of your screen, where we used a laptop as a high-speed data recorder to collect and store these data samples for the later processing that we did. And you can see the size of the ASR 2300 relative to the laptop. It's a small box around the size of a deck of cards. And we used a simple L1, CA, and PY patch antenna that you can buy on our website for about 25 bucks, and we put it on the top of a car and we drove around. And this plot or chart describes what I like to call the Woodinville loop. The yellow arrows indicate the direction of travel that we collected data as we drove around in our car, and you can see where we started and stopped collecting data on the Woodinville loop. And there are a few interesting artifacts in this loop. The blue track represents what code correlation GPS tells us when we process that raw data stream without any sort of interfering sources or a jammer being present. And this is just purely code correlation that you see. Well, near the top right-hand side of the plot, there are no dots on top of the blue line. That indicates that we didn't have a navigation solution at that point. And the reason for this is pretty simple. We passed underneath a highway, and we lost all of our satellites, and we had to go through a reacquisition sequence. Now, this track, this real-world data that we collected, has all the blemishes of real-world data. We had GPS visibility issues because we passed by an embankment, we went underneath the highway, we passed by semi-trucks, which limited GPS visibility. But ultimately, this plot shows you what that real-world data shows us, and this is what code correlation gives you. So we take that real-world data and we wanted to add a jammer. Now, since we couldn't physically go outdoors and do it, we used a software simulation to add it to that raw sample stream that we collected outdoors. And we wanted to simulate a real-world jammer. So we simulated, for this particular case, a 2 microwatt power EIRP jammer. That's a chirp sweep jammer. And I'll describe what that means on the next slide when I talk about the signal characteristics of what we actually simulated. And what we've been developing at Logtronics is a toolkit to actually test our hybrid navigation sensors capability to survive a jam attack. And to do so, we built up our capabilities to simulate a jammer and place it somewhere with respect to the data that we collected. And that's what this chart shows. The figure at the right, you can see that we placed a jammer near the bottom left corner of the Woodinville loop, and the left shows you how the J/S ratio varies with respect to time and distance. And as you would expect, the J/S increases as you get closer to the jammer, which is very typical or realistic for a jammer. If you get closer to it, it's going to become more powerful, and this was intended, of course, to test our hybrid technology. Now, as far as the characteristics of the jammer that we simulated, well, this chart shows that. We show you in both the time and the frequency domain what we simulated and what we added to our raw sample streams. This is a chirp sweep jammer, and it's intended to wipe out L1CA, just like the ones that you can buy online. Now, the reason it's called a chirp sweep jammer, well, you can see that in the left-hand plot, the frequency varies from -6 to +7 megahertz, and then it reiterates in this sawtooth manner. And on top of the blue line, you can see a red line that represents L1CA, and this is where it's knocking out the L1CA code correlators. The right plot shows you the spectral content of the jammer when we're close to it, when we're at 25 dB J/S. And the one thing that's interesting to note in this plot is that when we're close to the jammer at 25 dB J/S, the spectral content of the jammer begins to rise above the thermal noise floor, and you can actually see it. Now, we don't have any noise plotted in here. This is just to characterize the jammer that we simulated so you can see what it looks like in both the frequency and the time domain. But we took this jammer and we added it to our raw sample streams to see how it affects code correlation and our hybrid receiver. And this is what it does to code correlation on the Woodinville loop. As we drive around, we get closer and closer to the jammer, and ultimately the code correlators fail. We lose them at 23 dB J/S, and we don't recover for quite some time. And this is before the point of closest approach. Eventually, we round the corner, we pass by the jammer or the point of closest approach, and we start putting distance between ourselves and the jammer as we progress around the Woodinville loop. And eventually, as we get farther away from the jammer, our code correlator recovers and we start naviging again. Well, this is not very useful, this navigation outage for something like a commercial UAV. And the question remains, what happens when you use hybrid technology in the presence of a jammer? And we'll show you that on this next slide. So when we were describing the characteristics of the jammer, there's a point at which, using our hybrid technique, we can detect it before our code correlator fails. And more importantly, we do something about it. We switch to a hybrid mode, which is denoted by the red line in this plot, to survive a jam attack. So when we see that there's a jammer present and it's going to interfere with code correlation, we switch to hybrid mode, and we survive a jam attack. We round the corner, and once we put some distance between ourselves and the jammer, we switch back to code correlation. And you don't necessarily have to switch back to code correlation. For the sake of this particular test case, that's just what we did. We could have remained in hybrid mode, but since we are far enough away from the jammer, we said, hey, let's go ahead and switch back to code correlation. But the one takeaway from this slide is that we survive a jam attack by not using some of these alternative techniques that are out there that Pete and Mike were talking about, or Frank that was talking about. For instance, we're not using a phased array antenna, and we're not using SAASM to survive a jam attack. So we're pretty excited about this because we can show that we're increasing the J/S margin of survivability And this is just one particular test case from the preliminary testing that we've been doing, but through additional simulations, we've been able to show that we can significantly increase the JRS by somewhere between 15 and 20 dB compared to a conventional COTS GPS receiver. We can also detect interference before your code correlator fails, but more importantly, you can do something about it. We can mitigate failure by seamlessly switching between operating modes and the data types that are available to us in this hybridized architecture. So this makes it a more robust and resilient solution for something like a commercial UAV where you don't want to suffer navigation outages. And we're doing this without SAASM, but we're approaching near SAASM JRS performance without crypto key access. So we're really excited about this. And these are preliminary results, but we're going to be doing a lot more testing in the near future. And if you guys, I know I blew through this really quickly. If you guys have questions for us, we're going to be at JNC at booth 31. Please come talk to us. We're really excited about this, and come say hi.
Thank you, Michael. All right, we're just about ready to open up for questions. I would like to throw out one last polling question, if that works for everybody. And let's see, here it comes. How would you classify your organization business? Location sensor solution provider, navigation system provider, payload and avionics systems integrator, or academic and corporate R&D? All right, so academic and corporate R&D is the winner, and very good. All right, well, we're going to move into Q&A at this point. If you've got any questions, now's a good time to present them. Come on, machine. There we go. And let's see, our first question is, let me just check on the priority here. Our first question is, where did you implement the delay baseband RF in order to generate spectrum compression? The delay comes at baseband. We've got a lot of published papers out there on SCP technology if you're interested in more about how it works. Also, you can look in our patents as well. That describes that more clearly. There was a next question that said, what is the jammer signal model? I think we covered that in the presentation. It's a chirp sweep jammer. So basically we sweep a carrier wave from, I think, a minus
6 to plus 7 megahertz.
Minus 6 to plus 7 megahertz over a 9
microsecond period.
9 microsecond period. Thank you. And then we adjust the power based on the apparent JRS that we're trying to attain between the jammer and the receiver. Another question out there asked, why is SAASM considered anti-jam? Yes, it is great for anti-spoof, but there is nothing inherent in the encrypted signal that helps with AJ. In fact, it may be a bit easier to jam. The SAASM signal actually does have anti-jam qualities to it because it allows you to access the PY channel using a FOID correlation methodology. And then using that, you can increase your coherent integration on the PY channel, increasing enhanced process gain and narrowing up your effective post-detection bandwidth. That capability has allowed the Dagger receivers and even other receivers to achieve J/S margins approaching 45 dB J/S, and I think I've seen some papers claiming that they've got 60, though their results are dubious about how they arrived at some of those implementations. There's a lot of papers from 10 years ago claiming they could do 80 J/S margins with it. I have not seen direct evidence that they in fact ever accomplished that. But in any case, the reason that you can get anti-jam qualities on the PY better than the CA is the ability to get better isolation because of longer code lengths, higher code speeds, and as well as coherent integration time. There was a short question which I probably should have answered in during Pete's presentation. Is L2 a typo? Probably is. I'll have to go back and look at what that is.
Well, it depends which one of the internet purchases you actually make.
Yeah.
That there is one of the inexpensive ones that goes after L2 simultaneously.
Yeah. The interesting thing is that there was a survey of commercially available jammers done by Cornell in Texas, done I think in 2012. I think that was when that paper was published.
11 or 12.
They were publishing over, I think they had 10 different jammers they had purchased. And it was interesting, while a third of them were single frequency, primarily L1, but another third of these units were multi-frequency, both L1, L2, and then even some of them were even doing cellular signals simultaneously. And it was Pete was very correct that the expense of doing multi-frequency is actually dropping very quickly, as we have found developing SDR technology. It's not a big stretch to do multiple frequencies anymore. So multi-frequency jamming going forward is going to be a definite case.
And every time another navigation constellation comes into existence and looks to be useful, you can bet that the jammer industry will be on it like ants at a picnic.
Lots of good questions coming. Give me 1 second just to sort them out. Okay. The next question is, what techniques that you have shown here to be applicable to automotive environments? For example, jamming of autonomous or connected vehicle navigation. Essentially, since we're not great pilots or anything, we're actually testing all of our technology basically using an automotive environment. We believe targeting an automotive-based implementation in an autonomous sense is actually the best way to build up a good technology base. When you get to adding ability to go to a connected car or network base where you get assisted GPS, you can greatly enhance your acquisition capability. For autonomous vehicles like UAVs, we've wanted this receiver to basically get started up on its own without any external requirements. But when you bring into the idea that you've got an external network capability using assisted types of technologies, getting a faster acquisition is certainly a possibility, where you can also probably increase your acquisition performance better than you might without it. So by getting into a connected car or network-based solution, the shorthand version of saying is that you're going to improve your acquisition capability in an interference situation. You still need to design your receiver to actually support anti-jam or a higher J over S type of performance in those situations, but ultimately you can acquire faster or reacquire once you get into a safer location. There was a question here. How do we tackle precise offshore navigation issues at high latitude? I'll throw that out to the panel because I'm not sure if I understand what he's asking. Going to give that one a shot, Pete?
I'm trying to think of, sort of like pipeline operations or oil tankers up in Arctic latitudes. I can see that. I think the situation is very much the same as goes on at the lower latitudes.
I mean, obviously GDOP is an issue, but
you're going to have an awful lot of satellites available, and that will help. And the determination of the vertical, for example, when you're at sea, a lot of the mystery's gone out of that.
Right. Very good. If we didn't answer your question well, please email us after the fact, and if you can clarify for us, we'll provide a more thoughtful answer. The next question is, a state vector message type from GPS could provide enhanced performance in weak signal interference in prone environments. Yes, there is some validity to that, but the question is how much additional JOVRS could that provide?
And can you extract a telemetry
right.
message?
Yeah, your receiver has to be able to extract that message in those situations. The next question, is an IMU component connection to your device plug and play or need to be configured? I'll field that since I actually wrote that software. At the current implementation, we would need to be configured. We will strive towards a plug-and-play implementation. It's basically a serial interface. But in the long term, we would strive for an automatic integration with some standardized high-performance IMUs. And I think that culminates most of our questions at this point. And I'm going to go ahead and hand back to Bethany, and we can wrap it up. Actually, a bunch more questions just came in.
All those cards and letters.
Yeah. The one question, is it useful for as road work and tunnel work? The anti-jam qualities of the receiver, I think, wouldn't improve or hinder necessarily road and tunnel work. It might improve it a bit. I think you'd be probably more interested in talking to us about some of our signal of opportunity implementations with the same technology that would allow you to utilize other types of signals when you're in a truly obstructed situation where the GNSS systems are not available. I think that's it. I'm going to go ahead and hand it back to Bethany now for a wrap-up. Thank you very much.
Thank you, Mike, and thank you to our audience for attending today's webinar. As you'll see on your screen now, you have email addresses for all of our panelists today. Feel free to reach out to them individually if you think of some questions you may have had that didn't have a chance to ask here today, though they are interested in hearing from you. And thank you again for attending today's webinar. An on-demand recording will be emailed to you in 2 weeks and will be available at gpsworld.com/webinars. And while you're there, if you missed our May 8th event, Data Capture for Geointelligence, it is now available. The event featured an in-depth portrait of geospatial technology unheard of just a few years ago, along with never-before-seen video footage provided by Cyclomedia and Soft Power Solutions. We also have several great events coming up this summer. Please join us for our next event, How Much Farther to the Promised Land? Purchase Decisions in the Evolving Landscape of GPS, Multi-GNSS, and Alternative PNT, scheduled for Thursday, June 5th at 1 p.m. Eastern Time. Just today, the speakers for this webinar were announced, and they include Steve Alt, an expert on radio-based technologies from NAVCOM, John Pottle, a fellow of the Institute of Engineering Technology, Philip Matos, chief architect of ST Microelectronics chipsets and consultant to several chip manufacturers, and Paul Ben-Shuf of Licata. Then coming up in July, we'll be hosting our first ever webinar live from the show floor at the Esri International User Conference in San Diego. Look for more on that one coming soon. Again, you can register for these upcoming events or view previous events online now at gpsworld.com/webinars, and we look forward to seeing you there.